In this nugget, you and I are going to discuss and verify the address resolution protocol that's used by IP version 4. Let's begin. One of the challenges a device on an IP version 4 network faces is that as it does the encapsulation process, maybe we have an HTTP request that's going down the protocol stack, it gets encapsulated at layer 4, becomes a segment. It gets re-encapsulated again at layer 3, now it becomes a packet. Once it hits layer 2, and it needs to be encapsulated, and we need to add the layer 2 information, the source layer 2 address and the destination layer 2 address, how in the world does our computer know what the layer 2 burned in address is on some other device that's on that same network? And the answer is, by default, it does not know what the layer 2 address is of the other device on that local network that it wants to communicate with. And that's why IPv4 has this really cool protocol called ARP, Address Resolution Protocol, that allows a computer to dynamically learn the layer 2 address, the MAC address on Ethernet, that maps to a corresponding computer's layer 3 IP address. So as an example, let's take computer 2 right here, and let's say computer 2 has the IP address of 10.1.0.101. And this router, which is on this same network segment right here, along with all these other devices I've just circled, is at the IP address of 10.1.0.1. So that's interface 3/0 on router 1. Now, for the purpose of our discussion, let's just go ahead and presume that the first two numbers here are the network, and that the last two numbers are the host, meaning the host address, the IPv4 host address of these interfaces on the network. Now, it's very likely that this computer number 2, when it was being configured via DHCP, it learned about the default gateway it should use if it ever needed to communicate off of the local 10.1 network. And for our example, let's presume that this computer just wants to communicate over to router 1. Maybe it's going to do a ping request just to verify basic connectivity. So as that ping request is being encapsulated, computer 2 says to itself, I'm on network 10.1. The destination I'm trying to reach is also on 10.1. That means he's on the local IP subnet, same network as I am. But now I need to know his layer 2 MAC address, so that as the encapsulation happens at layer 2, this computer can go ahead and correctly add the source MAC address of computer 2 and the destination layer 2 address of the router's interface. So what computer 2 does to discover the layer 2 address of the router interface, it's going to do a little shouting. It makes me want to shout. And the ARP request is going to send out something called a broadcast. A broadcast is sort of like an all points bulletin. So with the broadcast, everything on this local network here, the 10.1 network, would see and have to listen to that broadcast. That means computer 1 had to process it, the printer had to process it, the signal was sent out to the wireless access point, which in turn was also received by a computer on that wireless network. This internal server had to see it, and the router had to see it. Now, as you can imagine, sending a broadcast takes a little bit of toll on everybody who has to look at it. And that's because everybody who receives that broadcast frame is going to have to de-encapsulate it to see what's inside. It's like reading a book. Oh, here's the intro. Interesting. I'll keep reading. And computers, they keep on de-encapsulating, or they keep reading until they either get something that they can process, or they realize it's not for them. For example, if I went into a bookstore and said, hey, this looks like an interesting cover, and I open it up and I say, oh, this is about rocket science, I would go ahead and close the book. I'm done. That's not my topic. And that's effectively what all these other devices did except for the router. And that's because this router as it started to de-encapsulate that frame, this broadcast frame, and started looking at the contents, it saw, oh, this is an ARP request, and it's looking for the person who has 10.1.0.1. And router 1 said, that's me. That's my IP address. And as a result, router 1 responds back to computer 2 to indicate, hey, buddy, I understand you're looking for the layer 2 address associated with my IP address. I have the IP address, and I'm responding to you so that now you know my layer 2 address as well. So here on Bob's computer, let's do a couple of things. Let's do an IP config just to verify that we do have an IP address. And sure enough, our address is 10.1.0.101. And we've been configured to use a default gateway of 10.1.0.1. And this default gateway IP address is the IP address that R1 is using for his interface connection to this same network. Now what's interesting is if we want to see what we've already discovered via address resolution protocol, we can use the command ARP -A. I haven't learned about the layer 3 to layer 2 mapping yet for my default gateway. But check this out. If we did a ping to 10.1.0.1, which is the IP address of our default gateway, that will trigger in the background an ARP request so that we can learn what that layer 2 address is of our default gateway. And assuming the ARP is successful, we'll then be able to go ahead and do the ping requests because we'll be able to correctly encapsulate at layer 2 with the destination layer 2 address of who that frame is for. So we'll do our ping to 10.1.0.1. And I'd like you to notice something interesting. At least I think it's interesting. I hope you do too. And that is our first ping, it took 61 milliseconds. So as far as milliseconds go, there are 1,000 milliseconds in 1 second. So it's all happening pretty quick, but that first one, the ping took 61 milliseconds to respond, and then the last 3 took 31 milliseconds. Almost half the amount. Why? Why so much additional time for the first ping? And the answer is, it was waiting for the ARP resolution to finish. So if we were going to do a ping again, I'll just use the up arrow key and do a ping to 10.1.0.1 once again. You'll notice that this time, each of the ping responses are about equal. And that's because when we do an ARP request, when a computer or a computing device does an ARP request, it doesn't forget that information immediately, it caches it. So if you use the up arrow key a few times and do the ARP-A again, you'll notice now that we have a mapping that says, hey, the 10.1.0.1 IP address, the layer 3 address, maps over to the layer 2 address of 000501010101, which is the layer 2 address that R1's network interface card is currently using on our local network segment. And over here on the right, it indicates that that was a dynamically learned layer 3 to layer 2 mapping, courtesy of address resolution protocol. And one other note that is also interesting is this. Notice here it says physical address. And because it says physical address, sometimes we think, oh, is that like the physical layer of the OSI reference model? And the answer is no. A MAC address, a layer 2 address, unfortunately, but actually sometimes also referred to as a physical address. So don't let the word physical throw you off as far as where that is in the protocol stack. It is absolutely a layer 2 address in our TCP/IP protocol suite. Now, if we had captured that ARP request, and we did, it would look something like this. If we look at the details of the payload of this ARP request, it indicates a few basic things. First of all, this is a request. This is ARP trying to discover the layer 2 address associated with an IP address. Next, the person who's sending this request has a MAC address of this guy right here and an IP address of this right here. And the benefit of sending this out in conjunction with the ARP request is that the person who gets it In our example, the router can just put that mapping between the layer 3 address of computer 2 and the MAC address of layer 2 in its ARP cache so that it doesn't have to do its own ARP request. And then here in the target is specifying I'm looking for the layer 2 address associated with 10.1.0.1, and currently I don't know what that layer 2 address is, so as part of the request, I'm just going to put all zeros here. And a MAC address, a layer 2 MAC address, is 48 bits in length, but we often represent them in hexadecimal, which we'll cover in more detail in another nugget. Also, if we look here in the layer 2 header information, it shows the source MAC address of the person sending this is the same MAC address of the person requesting it. So these two should match right here. And the destination layer 2 address is a broadcast. And a special address for a layer 2 broadcast is 48 ones. Or represented in hexadecimal, that would be 12 hexadecimal F characters representing 48 ones. So any device who receives a frame of data where the destination layer 2 address is all ones in binary or all Fs in hex, they're going to start to de-encapsulate those frames to see if there's anything relevant for that device in the payload of this frame. So fortunately for computer 2, R1 heard that request and responded with an ARP reply. And if we look here at the layer 2 information, router 2 sourced this from his own MAC address and sent it back to the MAC address of computer number 2. And this is what's referred to as unicast, meaning it's not meant for everybody like a broadcast, it's intended for a specific destination. So an ARP request is broadcast and the reply is unicast going back to the requester. And that way, we don't have to bother all the other devices on the local area network who really don't care about our little ARP conversation that we're having. So we're saving all the other devices a little bit of overhead by sending the reply back unicast as opposed to sending a reply that's destined to the layer 2 broadcast address again. And in the payload of this reply, the sender is indicating his IP address. This is R1's IP address as well as R1's MAC address, which was the whole purpose for the ARP request in the first place. Computer 2 wanted to learn the layer 3 to layer 2 mapping, specifically the layer 2 address of its default gateway, and now it has it. So for future frames that it sends to the default gateway, it can address those at layer 2 using the router's layer 2 address. And if I remove this filter that I currently have for this protocol analyzer, we can see the ping requests and replies starting here in number 5. And if we look at layer 2 of that first ping request, it's being sourced from the layer 2 address of computer 2, and it's being sent to the layer 2 address of the router. In this nugget, we've discussed and demonstrated how we can do layer 3 to layer 2 mappings from an IP address to a layer 2 MAC address on a local Ethernet network segment. Here are the hands-on practice that I would love for you to do before you go to our next nugget together, and that is this. Number 1, I'd have you run ipconfig on a Windows computer. When you run ipconfig, you'll see what your IP address is as well as your default gateway. Then I'd like you to go ahead and do a ping over to the IP address of your default gateway. And if your computer didn't previously have an ARP entry in its ARP cache for your default gateway's layer 2 address, it will now because of the ping that you just did. And then finally, I'd like you to take a look at your ARP cache by using the command ARP space -A. And that's your homework assignment from this nugget. I have had a great time in this nugget. I'm glad that you joined me for it. I hope this has been informative for you, and I'd like to thank you for viewing.